Good afternoon. I hope you had a nice coffee break. Welcome to my talk. This is user behavior analytics for cybersecurity and its implementation in Scala. My name is Derek Lin, the chief data scientist from Exabim. As Domingo said earlier this morning, we are a cybersecurity company working in this area, right? And today I'll be co-presenting with my colleague here, Leonid Kladko, who is also a Scala developer here at Exabim. So this is the content of the talk I want to go through today. My guess is many of you do not have a lot of background in cybersecurity. So cybersecurity has many different areas, and detecting insider threats is one of them. Today I'm going to go into that. How do we build a system to detect insider threats, and specifically how we use user behavior analytics to address that. And then after my turn, Leonid is going to talk about how we use Scala to build the data processing pipeline. Before I turn to talk about another use case of a data science application and for cybersecurity. Before Leonid again talk about how we go about doing the implementations. All right. So cybersecurity comes in many forms, and one of the important area is insider threats. What is insider threats? Let me describe you quickly here. Insider threats are the legitimate employees or people who have access or credential to the network. These are the people who have the keys to the kingdom. Once you have the key to the kingdom, you can do a lot of bad things if you have a malicious intent. So who are these people, right? These people are folks that are like disgruntled employees. This might be internal employees that they access data with malicious intent. Or this might be, again, internal employees or external contractors who work with the company, but they do have a lot of privilege, in the network access, but they are using the network environment in such a way that that violates acceptable user policies. Okay, and the third buckets for insider activities are external adversaries who compromised legitimate user credentials and coming with a malicious intent, most likely via phishing activities. And once they get into the network, they can start doing bad things. Now, I don't need to tell you how serious the problem is, because cybersecurity threats, it's all over the news these days. But if we are going to put a dollar figure to the threats caused by insider threats, 2 years ago there was this company that did a research over a large number of large corporations, and they attached a dollar figure like something like $4.3 million per year being spent per corporation on the average, right, to detect insider threats. Now, of course, this number varies depending on the size of corporations, but if we want to put a dollar figure on it, that's $4.3 million, which is a lot, and that's why we want to study it and try to detect threats early. So how do we go about doing it? Because we are talking about using machine learning in order to perform user behavior analytics. Everything starts with data. Okay. So first of all, we want to collect as much data as possible from as many varieties as possible in order to achieve what we call the 360 degrees of a user behavior. So what are these data? One example might be Windows activities. I mean, users asset accessing activities. Typically, that is recorded in something called domain controller. This is where, with this log data source, you can see which user is accessing which assets. With that kind of records, that allows you to profile the activities of a user behavior on the network connections. Or you might have a VPN log. This allows you to see which user tend to come from which countries, and that, again, that allows you to profile their VPN activities. And these are not the only two, right? I mean, we are talking about database logs, file access log, cloud application logs, and physical badging access logs, and so on and so forth. With all these data sets, then you get a better insight to what the user is doing on your network. Now, so as I said, it all starts with the data. Here I give you some examples of data sources, messages. We have Windows log, we have VPN log, data log, and batch accessing logs. These logs oftentimes it takes some spatial knowledge in order to parse the data sets. As we are receiving the data, as the system is receiving the data, all this data, all these events need to be parsed correctly with the proper domain knowledge. And this data set does have what we call the big data problem. Specifically, I'm referring to the 3V effects, right? We have a volume, variety, and velocity. This data is very large in volume. We have seen something like 5 terabytes a day of data coming through the system. It also have a very high variety. Earlier, I showed you some examples of data sources. We can potentially talking about 20 to 30 different data sources that we should try to inject. Then the data is also have very high velocity. We are talking about 30,000 events per second to 70,000 events per second that we need to process. So in order to make all this work, all this data that's coming in need to be processed in real time. But dealing with the basic 3V effects is not the only issues, because all these data sets, all these events, they can come into your system out of time order, and you do need to store them in place in order to stitch your events in a coherent manner. So we need to processing the events so that we need to do sorting in time. In addition to that, some of these events are not stateless, right? Some information in these events need to be extracted from another events in an earlier time. So we need to do cross correlation across events. So it doesn't take a lot to think that this is actually a lot of things going on as you are ingesting data, try to process all these data sets, parsing, sorting, and normalizing your events before you can massage them into a nice state that you can start doing behavior modeling. All right. So once we have all that data set carefully parsed and normalized and correlated, then only at this time we can begin to talk about behavior profiling. What do I mean by behavior profiling? Right. So for each user, I want to profile his behavior across many dimensions on his activities. If I can establish his normal behavior profiles, then next time when I see some new activity coming from him that cannot be explained by his profile, then that is the basis for me to raise an alert. Something's wrong, something's anomalous. Okay. So let me show you some examples of a behavior profile that I'm talking about here. Let's say, for example, from the VPN, we can see over the, say, 6 months of data, we can see how often he is coming through US. So in this example, he might be coming through US 71 times, coming from UK 33 times, coming from France 1 times. So over a historical data, we just profiled his behavior on the VPN, the source country, so that we can use this for later anomaly detection. Of course, we just defined his activities over the VPN logs, but we can also do the same on what he's doing over different devices that he has touched. So on the x-axis, instead of having countries name, you might have device names, or we might have we might want to model the way he's using the application in the past, or his executable processes. So all these behaviors over the data logs can be modeled with histograms, and these are what we call the categorical data. Instead of categorical data, we can also do his behavioral profiling using numerical data, where instead of profiling the activities over discrete entities, we can profile over the numerical properties of his activities. For example, we can know what is in his normal patterns of a number of logons that he performs throughout the session that he is in, or or the number of bytes that he has sent through emails, or the number of emails he has transmitted, and also how long the session duration is. That typically characterize his normal behavior. And in addition to categorical and numerical data, we can also profile his time of the week data. This is where we can kind of see what is normal active hours over a certain set of activities. So in this example, we have VPN activities, and you can see that his normal activities goes from 8 a.m. to 8 p.m. We can do the same thing for building access activity and also file activities, right? So we have seen in the past, for each user, we can potentially build 400 or 500 such histograms. Each histogram will characterize a certain dimension of his behavior. And once we have this histogram built, then at this time we can talk about how do we use them to do anomaly detections. Here's one example. So throughout the course of his session events for Victor, he did many activities over these sessions. But one of them, when he tried to access an asset on the network, this particular asset access cannot be explained by his profile. Okay, so maybe he's touching an asset that is new, never been observed in his profile histogram. Okay. When the histogram cannot explain his activities, we raise an alert with a score. In this case, we say, okay, give him 15. For Mary, she might trigger additional alerts, right? Because three other activities on these sessions cannot be explained by her histograms. So in this case, the first alert might be, okay, the fact that she triggered the first logon to an application from a location. Maybe we give that 30 points. And the next activity that she had, she might be coming from, she might have an abnormal repository access to a GitHub, and they say that's another 30 points, and so on and so forth. And the result of that is we simply aggregate all these scores corresponding to the alerts that she has triggered and sum it up, and she will get a 95 score for this session, right? And for another person, John, he might trigger 120 score. So at the end, we would, as a security system, we would simply present the sessions with the highest score for the security analyst to continue do the forensic investigations. Now, trust me, I have just oversimplified the whole system a great deal, right? To do all this, in fact, you need many different components, right? So here we have this architecture that try to do what I just described. And this architecture actually composed of multiple engines, right? So on the graph here, you can see that as the data coming in from left-hand side, the first thing the first engine that received this data is called log ingestion engine. It will try to do all the data processing I mentioned earlier, right? To sort, to normalize the events, and to cross-correlate the events. And then all these events need to be processed in real time. After the log ingestion engine is finished with digesting the events, next it needs to be processed by the context building engine. This is where, for each event, I want to enrich the context by providing additional information to each event by saying that, okay, on this event, if I see this particular machine, I want to know whether this is a server or a workstation. This account for this event, is it a normal user account, or is it a service account? Okay, all these different contexts, they play different role in performing anomaly scoring and also for security forensic. Once these events are processed by the context building engine, it gets sent over to the session building engine, and this is where we stitch together all the activities from the session from the start to the end in order to assemble the activities into a coherent structure, and before tying them together and present to present them to the users. So only after this, processing steps, I can now start talking about the behavior profiling engine that I discussed earlier, and as well as the anomaly detection engine I talked about earlier. What I'm showing you here is the online real-time processing pipeline that allows the events to flow from left to the right. How do we make that happen? We actually leverage things in Scala to control the data flow. And this is something that Leonid we're going to show you later. But in addition to the online real-time processing engine, there are also many things in the data science realm that should be done in the offline basis, okay? That we do not need to be constrained by the real-time requirements of data processing, right? So if we can do things in real time, if we can do things in offline, we can enable additional, data science applications. And one of them is it's another way of doing anomaly detection, which I will present in the second part of the talk. And now I'm going to turn over the podium to Leonid for him to talk about how we use Scala and Akka to enable the processing pipeline in real time.
Okay, thanks, Derek. As you noticed, Exabeam is all about data. So I'm going to give you a quick introduction how we do data processing and explain some basic concepts on the way. Okay, let's imagine you want to apply some computations in parallel, and for some reason, Scala parallel collection is not enough for you. So at first, you will try to find some existing tool and will be overwhelmed with variety of choices. But you have more chances to make the right choice if you understand the main differences between them. So at the beginning, you need to look at your data and your problem and choose one of the following execution model, batch or streaming. Batch means processing of non-continuous data. So if you have some historical or archive data and need to apply some analytics on top of it, we will go with batch. For example, in Exabeam, as soon as we have a complete set of data for a day, we run some Spark jobs. Okay. But for some problems, we want to process our data in real time as soon as it's been produced. So in contrast to batch, streaming pipelines requires a continual input and usually process one events at a time. But it's not true for all frameworks. Some of them, for example, Spark streaming use micro-batching. Micro-batching is a technique when we combine some events into small batches and deliver them to batching processing framework. Now let's talk a bit about performance. In terms of streaming, here we can use a pretty familiar characteristics like latency and throughput. To illustrate it, let's come up with some artificial example. Let's say we want to build some stock market prediction engine. We receive market prices in real time, update our model, and produce some forecast. And this forecast is valid only for a fraction of a second. So in this case, we need to concentrate on a low latency. And for example, micro-batching might not be the best choice for us. On the contrary, in Exabeam, we analyze user behavior as a sequence of events. So in our case, latency is not so important, but we have huge volumes of data, so we are concentrated on throughput. Okay. It also worth to mention how of these frameworks actually parallelize computation. And here we need to understand the difference between data and task parallelism. Data parallelism means that each course execute exactly the same set of operation on some small on a small portion of data. For example, this approach utilizes batch frameworks like MapReduce or Spark. Task parallelism in turn focuses on executing each operation in parallel. One more thing which worth to mention is that sometimes the single machine cannot handle huge volumes of data. So we might need to scale out and run our system on several machines. Most of frameworks actually supports clustering out of the box, but for example, Spark streaming hasn't supported clustering yet. Let's back to Exabeam. Exabeam was found 5 years ago, and there were not so many choices as we have now. An early version of Spark streaming was considered, which biggest problem was lack of flow control. And in the next few slides, I will explain how we build our data pipeline on plain actors and explain what flow controls means. Just a quick recap on actor model. So what we know about actors, that this is a primitive of concurrent computation, and actor can do a few things like receive and send messages. It can have some internal state. It processes one message at a time, so we shouldn't care about concurrent access to its state. And also, of course, messages must be immutable. Let's try to build a data pipeline with actors. So here we have source actors, which basically just fetch data from somewhere. When source get an event, it sends it to the first processor, which in turn sends it to the next one, and so on until we eventually reach think. Think is an actor which does some final action like saving the results. But turns out sometimes this approach doesn't work. If we try to process even at fast rate, we will run into the problem called slow consumer, fast producer. If producer is too fast, consumer eventually end up with a full queue. Or in case if we use an unbound queue, we can get a out of memory error. So let's try to change it a little bit and replace it with pull-in pattern. Well, now let's make consumer to ask for more data when it's ready. So this approach looks better, but what if we have a slow producer and fast consumer? What should producer do with data request if it has no data to send? And in fact, we actually don't want to care about which one is faster. And actually, this problem is well known, and it's called back pressure. So on slide you can see a copy-paste definition of back pressure from Reactive Manifesto. So if you haven't visited it yet, so I advise you to take a look. You will find much more information there, and you can find out what reactive systems are. But now let's see how our back pressure works. Each node of pipeline has some buffer with data, and when buffer usage is below some threshold, we send a data request to producer, and we don't just ask for a single event. We specify some amount. And producer in turn accumulates that amount and push events to consumer when demand is above 0. We don't send data requests if accumulated demand is already high, because in this case case, we might overflow our buffer. Okay, when demand is equals to 0, it means that consumer buffer is almost full, and the producer buffer will grow respectively. So don't forget that in our pipeline, producer is consumer as well. So this behavior will propagate back to the source. Okay, now I hope you understand why backpressure is important. And as I mentioned before, we have some algorithms which are most suitable for batch processing, and Derek will show you one of them.
All right, thank you, Leonid. So I'm going to show you an offline batch processing data science use case or machine learning use case. And this is a good contrast to the detecting anomaly versus compared to the previous use case that was more of a real time. This one is offline. So what we are trying to do here is I want to detect anomalies on the day level activities, right? And the idea is to model the long-term behavior for pattern or volume change. Now on the screen here, if you see I guess without the pointer here, that each row is it describe the type of activities this user has done. For the columns, you can see that the user activity spans from day 0 to day, I guess day 29. Okay, each cell in the matrix indicates the volume of activities from this user from the particular activity for the row and on the particular day for the column. Okay, the higher the color, the darker the color is for the cell, it means the more activity there is on that single day for that particular activities. So from here, you can see that between day 0 to day 29, you can see that he more or less has a kind of constant activities over remote access and Kerberos logon and account switch activities. Don't worry too much about the event names, but just knowing that these are different activities here. Okay. The idea is once I can visualize and actually construct my data matrix over this historical period, given the next new days of data on the day 30th, you can see that day 30th looks very different from the past. Okay, how do I find a mathematical framework in order to say that the day 30th is anomalous compared to the historical period? And the way we do it is try to model all that historical data with a mathematical representation on the same data set. And when I say model, I'm referring to a kind of a succinct way of representing the data, right? By modeling this high dimensional signal kind of a data, we want to model it using a technique called principal component analysis. Not sure how much of a linear algebra you still remember or you forget, but let me kind of describe it to you what it is. PCA, or principal component analysis, is a way of projecting the high dimensional data to a lower dimensional data without projecting it so that you remove all the noise by retaining the most informative signals in your data set. Okay, so if I'm to do an analogy, you can think if I have a 3-dimensional object composed of multiple points, right, like my hand, right, and if I can just shine a light over my hand, and that would allows me to project my object on the 3-dimensional space to a 2-dimensional space. Okay, if I can find a proper angle to shine this light, then that 2-dimensional space image would have captured the most of my information in my 3-dimensional objects here. Okay, so that's the process of PCA. Okay, in the same token, given the previous matrix, I have a bunch of points. I have 30 days of points, and each point consists of a number of dimensions here. I want to project this data set from the R dimension to a much lower dimension data. And again, the way to do that is to perform PCA. And to perform PCA, we use this algorithm called singular value decomposition, or SVD, so that we can decompose the matrix M, which I described earlier, to 3 matrices, U, S, and V transpose. And then from there, without going into details, we can find another matrix, P, that is a lower dimensional representation of the original dimension matrix M. Okay. Once I have that lower dimensional matrix P, I can then use that to test if my current data's behavior can be explained by this model I just computed. Okay, and the way we do that is, again, as we say here on the screen, given a new base of data f of n, I want to see if it can be explained by P, which is again derived from the SVD or PCA, by this formulation that basically is what we call the reconstruction error. So without going into details, just know that the error computed is it's in that form, it's in that expression there, which basically measures how much is a deviation of your current activities to the model you just built, which should have explained the historical data. Okay. Now Leonid is going to talk about how we implement this in Spark and also show you some codes.
Okay. Keeping in mind that some of our clients have tens of thousands of users, we want to run this algorithm in parallel. Here just a quick introduction into Apache-Spark. The basic abstraction of Spark is a resilient distributed data set, or simply RDD, which is distributed collections of objects. All newer abstractions like data frames or data sets are built on top of it. Driver program is simply a process which executes our main function, and it's responsible for Spark context initialization, but all computations applied on RDD are executed on worker nodes, of course in parallel. I'm gonna show you how this algorithm can be easily implemented with Apache-Spark. At first, we want to count our event types for each user. So eventually, we will get a vector which represents daily activity for each user. Now let's take a look at our input. Here we are interested only in two fields, user and event type. And the tricky part here is to transform each event type value into a separate column. And here we can use a pivot function, which count events type for each user by event types, with each type as a separate column. So now we want to combine all of these vectors into historical matrix. But we need somehow to get all of those vectors for each date in our training period. And here we can apply a technique called window sliding technique. So instead of, so we can process only current day and save it. So we might use it for the next processing. And having all of our historic data, we simply combined it into two-dimensional array. Here you can see an implementation of daily activity change. We simply join our historical activity with daily activity, and then apply principal component analysis and compute reconstruction error. But since our algorithm heavily rely on linear algebra, we need to find some library for it. So we chose Breeze, which is a numerical processing library for Scala, and it has all necessary algorithm. Using principal component analysis, we are able to choose only the strong features of our model and reduce the noise. So we want to keep only top components, which total eigenvalues represent the majority of signals. So we actually can use an existing implementation of PCA, but in this case we needed to provide an exact amount of components we need to choose. So instead we implemented it using singular value decomposition. And the last step of the algorithm is to calculate a reconstruction error, which basically a deviation between our historical activity and the daily activity. And that's all about implementation of daily activity change. Derek will summarize our talk.
All right, by this time, I hope we have given you a good overview of what insider threat is and how we are trying to address that in both real time and also a batch offline basis. So at this time, we would like to kind of open up the floor for Q&A. Yes, go ahead.
What solution you use for offline storage, like database, or and why you choose it?
Okay, most of our logs we store in HDFS. Yes, because it's unstructured data, so we decided to choose
even
HDFS.
for offline, yes?
Sorry?
Even for offline.
Yes.
Okay, thank
I see.
Yes, thanks for the talk too.
Yeah.
I just wanted to know how you assess the quality of your models. How do you know if this an anomaly detection you're doing really detects an anomalies and not something else? How you measure this?
That's right. So one of the difficulty and challenge in cybersecurity is that we do not have a lot of ground truth, right? So the best we can do is flagging anomalies that are highly explainable. As long as we can explain that, then that's a job well done. Then that allows the forensic analyst to kind of follow through. By doing the visualization that I showed you earlier, it's fairly straightforward. I mean, it's very obvious, intuitive to see, the activities actually changed. Now, what to do next? Yeah, the analyst might start correlating additional events to follow up with the next steps.
Do you guys use any other ways to detect those kind of problems except like anomaly detection?
Oh yeah.
Like there's some patterns you just can look for activity for some patterns, like like if someone does this like login and this access and this, then it represents some kind of treat. So totally different from anomaly detection.
You mean like a storyline, like?
Yeah, I mean.
Mm-hmm.
Anything else except like this? This is like, I mean, that's good. Or just like, are there any other things you're doing to detect like problems with security?
It really depends on the use cases. There are many use cases in security. What I mentioned earlier is just one use case. This use case was suggested by clients, right? They said, it was inspired by clients. Another use case might be, say, for example, phishing domain name detection. Another one might be detecting anomalous usage of Windows command line executions. It kind of depends on what use cases we are going after. So for each one of them, it requires kind of dedicated data science effort. There's no single framework that fits all.
Yeah, of course. I was just interested in different things. Like, I mean.
Yeah. So actually, next week I'm going to Las Vegas to give another talk where I would describe a number of use cases that I have encountered. We can talk afterward. Yeah.
Thank you.
Mm-hmm.
Hi. So a question, much more a curiosity. How many tools do you have in-house to collect all of these logs from different data sources?
How many tools?
Yeah.
This tool is going to go.
Actually, we integrated with most popular log management systems like Splunk, Curator, and so on. So, and for each log management system, we write a separate parser and integrate with them separately.
did you have some plan or using unified tools for all of these data sources, something like the streams data collector or Apache NiFi?
I'm not sure if there is a way to unify this.
Yes, there is. Let's
okay.
talk offline. Yeah. Thank
you. Are you satisfied with Spark ML algorithms library?
Well, unfortunately, we don't use Spark ML so far.
So you use in-house implementations of algorithms, yes?
Yes.
Okay.
Okay, if there's no more question, I just want to have one comment. This area is very exciting these days in cybersecurity. Lots of things are going on, and our company Exabim is always on the lookout for good developers. So, if we are I guess I'm just calling you capable developers. If you have interest in this area, come to talk to us. Our booth is right outside. Thank you.